Thank you. Thank you. When I first learned statistical mechanics, when I was an undergrad, my professor told us two things. The first thing he said was that he doesn't know any stat mech. And he was trying to learn it along with us. So that went very well. And the second thing he told us was to think about whether life itself was a phase transition. So think about it. Maybe we're all novel phase of matter, right? Okay. So I'm going to dive right into it. Of course, out of equilibrium phase of matter, all life forms probably are, right? Strictly speaking, we're also quantum, right? With emergent classicality. In any case, it's a good question to ponder when you're a graduate student or postdoc, or when you're retired. All right. So I gave a generic title, Landscape of Quantum Phases and Phase Transitions, for my first lecture. I should say that this is, I'm really looking forward to these lectures. This is my third time lecturing at the Boulder Schools. I had tremendous fun on both previous occasions. I learned a lot, and I hope the students learned a lot from my lectures too. And one thing in terms of pedagogy that I learned is that I probably will not finish a good portion of what I've prepared to talk about, right? So I'm anticipating covering at most 2/3 or less of what I've prepared. So in particular, that means that I'll change the topics that I promised to talk about as we go along, because I anticipate there'll be lots of discussion and questions. Certainly, I would want there to be lots of discussions and questions. I get bored if I listen to my own voice for too long. So please speak up and help me listen to other voices. All right. So Sandy very nicely said at the beginning, this field of what's it called? Correlated electron systems. Was that in the title? Strongly correlated electron systems. Dynamics of strongly correlated electron systems. There's lots of frontier problems, and on which we need big breakthroughs in the future, probably coming from many of the people in this room. And what we would like to do when we lecture is to enable you to be able to make those breakthroughs in the future, right? So with that in mind, I thought I would sort of give you a random walk through some cool and interesting ideas in this very general field of strongly interacting quantum matter, and maybe you'll do something with it, right? So that's what I'm going to try to do in these lectures. So my focus will be on equilibrium, so no life, quantum phases, and phase transitions. So what is a quantum phase? So we'll take that to be the ground state of a quantum Hamiltonian. And actually, we'll take this quantum Hamiltonian to be a sum of local terms. So you might want to keep in mind something like a Heisenberg model, the Hubbard model, or things like that. For some phenomena, so these are obviously a sum of terms that each act locally in space. For some phenomena, it'll be important to include the long-range part of the Coulomb interaction, and we'll deal with it as we, meaning the community, deals with it as appropriate. Yeah. Finite temperature, we'll talk about the equilibrium state. It's not a ground state, right? So we just solve the quantum Hamiltonian and find its ground state, right? And in some cases, it will be useful to study toy models where every lattice site interacts with every other lattice site, simply because that may be a limit in which you can solve things and say something definitive. Right? But for the most part, we'll be interested in Hamiltonians, which are given as the sum of local terms. Right? And we want to understand the structure of the ground state, and we'll call that the quantum phase of matter. Okay, so my plan is to talk about the landscape of the various phases and phase transitions that you can have in a quantum many-body system of this kind. Now, there's many questions that one could be interested in this broad field. You might want to know how to characterize different phases of matter. You might want to know what phase of matter can exist in the first place, right? Given some microscopic system, maybe you have a system of bosons on a lattice, you want to know what phase it can have, and so on and so forth. You might want to know how phase transitions occur at zero temperature in such a system. You might want to know how to accurately compute the phase diagram of some model of such a system, right? Either numerically or analytically, how to probe the various phenomena experimentally. What probes are well suited to revealing which phase of matter any given system is in, right? So there are all kinds of questions, right? So obviously I won't cover all these questions. I'll talk about some subset in my talk. And through the rest of the month, you'll hear answers to many of these questions. So the plan of at least the first two lectures is first, we'll take a walk through the landscape. And provide some organization of the landscape, right? After doing that, I want to talk about some illustrative examples which will each serve a different purpose. And one of the things I want to emphasize in the first two lectures is how many aspects of the physics of quantum phases are strongly connected to each other, at least in an intellectual sense. So you might study topological phases, you might study Fermi liquids, non-Fermi liquids, quantum criticality, and all of these quantum Hall effects, and all of these things are strongly connected to each other. So it makes sense to have a global understanding of, of all these different kinds of phases and different kinds of phenomena. And you never know where the new insight will come from when thinking about a brand new problem, right? So at least that's the point of view that I'm going to take. So these illustrative examples, I will revisit old stuff, but from points of view that may be unfamiliar, at least to some of you, right? And maybe familiar to others, right? So the first thing I want to talk about is topological, which by now are 20 years young. Because the next topic I want to talk about is the fractional quantum Hall effect, which is much older than topological insulators. And finally, I want to talk about Fermi liquids. Right? So we'll go further and further back in time, but from more and more modern viewpoints, right? And see, just to think about it differently from how it was first understood. Oof, this is going to give me a workout. Resistance training. All right, so let's take this walk. So let's organize the different phases of matter into some broad categories, right? So first we can talk about conventional ordered phases of matter. So these are captured by the concept of broken symmetry, long range order. So an example will be a crystal, a ferromagnet, an antiferromagnet, and so on, right? Superfluids, dot, dot, dot. So these are collectively called Landau ordered states. So they were first systematically discussed by Landau, starting nearly 100 years back. And they're characterized by a Landau order parameter. I'm not going to spend much time on Landau ordered states, on symmetry broken states. I think that is the subject of any standard graduate condensed matter education. So let's move on to the next kind of phase. So I'll talk about non-Landau order. And I'll call this 1. And this is topological quantum matter. And it's known, so this has been known for millennia, right? Of course, solids and magnets, humankind is known for millennia, right? Topological quantum matter has been studied systematically, at least since the 1980s, following the discovery of the quantum Hall effect. So we'll call these, so these are ground states of many body quantum systems. With the gap to all excitations. So within this, it's useful to distinguish two categories. So the first is what's usually called symmetry protected topological phases, SPT. So examples will be the topological band insulator, the Haldane chain in 1D, and so on. Can I use this board or this? It's same, but this, yeah, okay. Slides up and down. So these are, in some sense, these should be regarded as trivial phases of matter in the following sense that, by definition, these phases have no exotic excitations. There'll be nothing with fractional charge or fractional statistics or anything that breeds in some way with anything else. There'll be, by definition, they also are states with a gap. But nevertheless, they can exist in distinct forms, and that's why there are distinct SPT phases. Right? Think about a topological band insulator if you wish. There's nothing exotic, there's no exotic excitation in the bulk of a topological insulator, but it's different from a trivial insulator, right? So phases with completely trivial excitations can still exist in distinct forms. That's one of the big realizations in the field. So I want to make a side remark just to be a bit more careful about terminology and definitions. There's a slight generalization of this notion of an SPT phase, which is often not made, but it's good to make. So we'll include phases gap phases with no exotic excitations that are protected even without any symmetry. So an example will be the Kitai-Majorana chain. So Majorana fermions on a lattice hopping with, say, nearest neighbor hopping, as several of you probably know, can exist in two distinct phases. In one, there are Majorana zero modes at the edge. In the other, there aren't, right? And there's no symmetry here other than energy conservation. Right? There needn't be any symmetry. So this general class goes under the name of invertible phases, invertible topological phases. It includes the SPT phase as a subclass. And it's called invertible because for any such phase, there's always an inverse phase, such that if you stack this phase with its inverse, the resulting combination is completely equivalent to a trivial state. Right? So there's this notion of an inverse for phase that exists in this category of phase of matter. Yeah. So just put the two things. So take a Hilbert space, the tensor product of two things, and then just put two different Hamiltonians such that the total, one sector has this as the ground state, and the other sector has the inverse phase as its ground state. And then you can deform it by doing some local unitary transformations to a completely trivial ground state. So you can trivialize, in this case, you can trivialize the boundary mode if you have two copies.
So item chain would just be another item chain.
Right, depends on that's right. With no symmetries, that's all it would be. Then you have two Majorana zero modes, which you can gap out.
Yeah.
Right?
But typically, how do you construct the inverse?
Oh, for that, I have to tell you first how to construct this phase, right? But which I haven't told you.
For SPTs, if it was
No, this is more general than SPT. This is the most general trivial phase. It doesn't need a symmetry to protect it.
Oh,
right?
Not contrasted with topological ones.
Exactly. So that's the next. And so talking about gap phases, these are the simplest possible gap phases, right? Nothing exotic, but still they can be in many distinct forms. Incidentally, after Leo's dictum, I hurriedly started typing up lecture notes. I've typed up maybe about 3/4 of what I wanted to say in the first two lectures. Hopefully, once I finish everything, I'll post it online. Yeah. Yeah, so fermion parity is sort of a weird thing, right? You can never break it in an electronic system. So for a single Majorana zero mode, but not when you have both zero modes, right? So in any real sample, it's not broken, right? It's something you can never break, right? You can't add an odd, yeah. So, but there are other examples like this, right? In every dimension, there are examples of this sort. It's a weird example in two dimensions with bosons, where with no symmetries, you can have a chiral edge mode. Bosons in some state which has a chiral edge mode. Yeah, and so there are things like that people have uncovered by playing around, right? So if you're talking about the overall possibilities, you have to include things like this. Okay, so let me return to SPT matter. So it's distinct trivial phases that cannot be adiabatically connected within the space for symmetry preserving gapped Hamiltonians. We had to draw a phase diagram, function of some parameter. We have distinct SPT phases separated by a phase transition. If you insist that this parameter G preserves the symmetry that protects these SPTs. Now, it may be possible to go around this phase transition through a path that breaks the symmetry, right, without closing a gap. But if you insist on the symmetry being preserved, there will be no path to connect these two distinct phases.
Broken symmetry phase.
Oh, broken symmetry, of course, requires the symmetry to protect the broken symmetry. Yeah. So the point is here the symmetry is preserved, but nevertheless the symmetry protects the distinction. Right?
The Hamiltonians be local here, or?
Yeah, let's just restrict for simplicity to local Hamiltonians. Now, novel phenomena happen at the interface between two different SPTs. As you know, for the topological insulator itself, you have SPT1 and SPT2, then something has to happen at the interface, right? And you can think of SPT1, a special case where one of the SPTs is just the vacuum. Think of the vacuum as the most trivial SPT. So then the boundary of an SPT with the vacuum, the boundary state will have to do something non-trivial, right? At least if the protecting symmetry is an internal symmetry. Okay. So that's the first category. The second category are topologically ordered states. And examples of the fractional quantum Hall states, gapped quantum spin liquids, and others. And so the most interesting zeroth order point to make about these topologically ordered states is that in their excitation spectrum, that's the emergence of sharp, well-defined quasiparticles with anyon statistics. Because strictly speaking, the notion of anyon makes sense only in 2 dimensions. But you can generalize it by saying that so long as this particle has a non-trivial braiding with some other object in the some other excitation in the system, we'll call that an anyon, right? So in 3 dimensions, for instance, you can have a particles that in topologically ordered states in 3 dimensions, you have particle-like excitation that also support loop-like excitations. When particles braid around with loops, you'll get non-trivial phases. So it's anyon statistics really is a way of saying that there's an infinitely long-ranged statistical interaction. And in addition, there's possibility of fractional quantum numbers. And this, of course, you know very well in the fractional quantum Hall effect.
So far, this includes super.
I knew that this would be a question. The superconductor is a bit subtle. In fact, I could give an entire lecture on where superconductors fit into this. I would put them in this category.
All of the things you've listed.
We have discussed it offline. We can discuss it offline. So the sense of the sometimes I think about the external electromagnetic field as a non-dynamical probe field, which is a physically correct approximation in a superconductor. Then it fits into this category, right? So let me work at, if you include that as a dynamical field that you quantize, then it's a different story, right? Yeah, but in condensed matter physics, we often treat the external electromagnetic field as a probe field. So let's work in that approximation, right? Which is good enough for condensed matter, right?
Three possibilities. It's a electromagnetic field to be fluctuating. So that's the case you don't want to consider.
Yeah.
It could be a probe field.
Yeah.
But it could also be dynamical in the sense of
a classical dynamical field,
classical
yeah,
dynamic,
which reacts to the dynamics of the system, yeah.
In which situation do you have to have this?
Where it's a quantum fluctuating field.
Sorry, not if it's not
To have not this, you have a quantum fluctuation.
Exactly, that's right, yeah.
Even if it's adjustable, even if it's classical, but responding to the
Yeah.
electrons, then it's still engaged.
Exactly, yeah,
Okay.
that's right, yeah.
As long as it's not dynamic.
Exactly, yeah. All right. Now, there's a low energy effective, yeah.
If I add something to these phases that, like some scattering from interaction between these quantum particles and they lose their sharp nature, like some that necessarily mean that the other properties?
No, so, so assume that excitations are all gapped, right? So the first excitation above the gap is going to be infinitely long-lived, right? And for simplicity, just think about interparticle scattering. Let's forget about impurities. Impurities, gaps can get filled in and things get localized. It's more complicated, right? Yeah. Now, so all these topological phases, you can ask about the low energy effective theory. It's a general folklore in condensed matter physics that the low energy universal physics of any phase of matter can be captured by a continuum quantum field theory, right? For topological phases, the natural expectation is that it's a special kind of quantum field theory known as the topological quantum field theory. It's very important in mathematical physics, and some of you probably heard of Chern-Simons theory, the past. So in general, that is true. But later on in this Boulder School, you'll hear lectures from Mike Hermele on things called fracton phases of matter, which are topological phases. Now, to what extent they can be described through a continuum quantum field theory is not entirely clear to me. And maybe Mike will address that question. It's a question people have thought a lot about over the years, simply because it's not entirely clear how to do it purely in the continuum. Right? And if it is described by a continuum field theory, it's a very exotic kind of continuum field theory, and there have been proposals in the literature. And maybe Mike will talk about it.
Symmetry not preserving information.
It-
Does it become like a trivial state?
Yeah, so that's right. Unless it belongs to this more general category of invertible phases.
Is it just like a
Sorry?
send the SPT phase into a trivial phase? Does it go through? I assume it does not go through a phase.
It doesn't have to go through a phase transition. That's right. Yeah. Again, think about a topological insulator. Can be smoothly deformed to a conventional insulator if you say break time reverse. Right? Yeah.
When we ask whether some phase is well described by continuum field theory, what questions are we allowed to ask? If we only calculate local correlation functions, I guess everything's exponentially decaying because it's all a gap.
Right. So topological phase has no non-trivial local correlation functions. So that's captured by the topological quantum field theory. There are non-trivial correlators, which are, loop string operators, right? So you can calculate their correlators. Actually, I meant to say this, but I forgot that your question brings us to memory. I'm sure all of you will use the bathroom multiple times. just in front of the bathroom, both the men's and women's bathroom, there are 3 wonderful posters. And I realized by looking at them just during this coffee break, that all 3 posters are deeply connected to what I'm going to talk about. I mean, hopefully you'll understand why and how it's connected to what you're asking about. Yeah. That can go on the t-shirt. Yeah.
There's always bulk boundary correspondence.
Yeah.
For the second type,
There is.
when do you expect bulk boundary correspondence to hold and when do you not?
So there is a more subtle kind of bulk boundary correspondence because there you have topological order in the bulk, you have something trivial outside. So the interface, the interface may be gapped, but even those gap boundaries of topological faces have interesting properties because there can be many different kinds of gap boundaries, right? Or sometimes the interface may be gapless, like in a fractional quantum Hall state. And then you know that there's interesting edge states. But there's a rich theory of what happens at the boundary of topologically ordered states. It's fascinating stuff, but I'm not going to talk about it. Yeah. Oh, great question. I will address it to some extent later on, but the quick answer, p-view of coming attraction is that you definitely need anyon statistics. That's the fundamental thing that enables the presence of fractional quantum numbers. Okay, if it's a true quasi-particle excitation. Other questions? Okay, so let me move on. So there is a side note that I should make. You know, as has been well known for millennia, broken symmetry states can coexist with each other, right? A crystal can also be a magnet. You know, superfluids can break translation symmetry close to Steve's heart. You know, pair density waves, superconductors can exist. You know, you have multi-ferroic order, people write millions of papers on such things. Now, the same story also holds once you include non-Landau order. You can have coexistence of different topological orders. You can have coexistence of topological order with trivial order, and so on, with broken symmetry order. All of those things can happen, right? No?
But how do you still have this like midpoint rule or whatever, the base coexistence?
Midpoint rule? What is the midpoint rule?
Common tangent.
When I say coexist, I'm not talking about, say, what happens at a first order transition. It's not like bubbles. So maybe we can think about that too. And saying just like 2 symmetries can break in the same material, you can have topological order coexisting with conventional order in the same material. There's nothing preventing it. Yeah. No. Right. But
Can you repeat the question?
it's asking, can you protect an SPT while spontaneously breaking the symmetry that's protecting the SPT? Right? I don't think so. Again, think about a topological insulator where you then undergo a transition to a superconductor, right? I don't think you protect, you do not protect the strict distinction from the trivial insulator. It doesn't become a topological superconductor.
I mean, related question is maybe differently worded. Is spontaneously broken symmetry in SPT identical to explicitly broken symmetry in SPT? That's what you're saying.
It's obviously not identical because you've spontaneously broken the symmetry, there's Goldstones and so on. So the real question is the following, right? So one way to probe the SPT is to introduce defects of the symmetry. You know, let's say you have a discrete symmetry, introduce a probe, a gauge flux for that symmetry. Now that translates into a topological defect if the symmetry is spontaneously broken. In the superconducting example, it'll be a vortex. You can ask whether the structure of the vortex, there's anything non-trivial about the structure of the vortex once it goes superconducting. I mean, in the superconducting state that knows about the fact that the parent band structure is topological. And the answer is no. In general, If there's no other unbroken symmetry protecting it, you can gap out. You can trivialize these topological defects, right?
Here for the FPT, that you have some randomness, but with the statistical symmetry,
Yeah,
that should be fine.
it depends, right? So again, there's a very elaborate and mature theory of that kind of thing in the last 3 years. I can go into that, but let me just say that it depends on exactly what the randomness is in. And there's a very detailed answer, but maybe it takes us too far away from what we're talking about. Yeah.
So the Chern insulator is SPT, so it's protected by a translator. Is that right? Or what's the
Right. So the Chern insulator, it's a very interesting state because it has a quantized electrical Hall conductivity, which is protected even when you break translation symmetry, right? But then maybe you won't call it a Chern insulator, you'll just call it an integer quantum Hall state. If you have some, say, randomness or something, right? But the fact that the integer quantum Hall response for the Chern insulator is much more robust than the band structure itself, right? In fact, the edge states are protected even when you break charge conservation because they're chiral. Yeah. Leo, and then, yeah.
Does mean that the interior on a figure is the same as the Chern figure?
Yeah, that's correct. Of course, to talk about the phase transition, I mean, as far as universal properties go, there's very little difference between a Chern insulator and an integer quantum Hall state. True, you have translation symmetry, but if you break the translation symmetry, then it just becomes the same state, right? Just realized in a different system, right? Yo.
Maybe I missed it. You said it, for the integer Hall effect, can you say where is it falling?
Yeah, so the integer quantum Hall, it's best to think about it as an invertible, lying in the category of invertible phases. The electrical quantum Hall effect depends on the conservation of charge. That manifestation of this phase depends on charge conservation. But you can break charge conservation, but you can't kill the edge state because it's chiral, right? So it will still be a non-trivial topological phase.
But somehow, so it's not topological order because all the exceptions.
That's right, yeah.
But you break the symmetry and there's something left over. So where is that falling?
So it'll be, it falls into this category of invertible phases. That's no non-trivial excitations.
But there's something still non-trivial about it in the sense of the edge, even if you break the U1.
That's right, that's right. So invertible phases in general will have something non-trivial at the edge.
But not if you break, okay, the conventional SPTs, if you break their symmetry, there's nothing left.
That's right. So in the,
Like this one is an example where you break the symmetry, the only symmetry, and there's nothing left. And there's something left.
right, that's because it's more than just an SPT, it's an invertible phase. The integer quantum Hall state is really an invertible phase where you can add an extra symmetry, which is U1, charge conservation, and then it leads to an experimental manifestation as an integer quantum Hall
Invertible
effect.
phase is bigger than the
Exactly. SPTs are a subset of invertible phases. Good.
Yeah,
the inverse phase would just be mu equals minus 1.
Exactly. That's right. Yeah.
What's the definition? Other than that, what is the definition of it? Any phase that can be trivialized?
That's right. Yeah. Any phase with no exotic excitations is gapped and which can be trivialized by adding a conjugate phase. There's a more precise definition, if you want, in the TQFT sense, that the low energy theory is some topological quantum field theory, and you look at its partition function on any manifold, it's 1. In its modulus is 1. Right? For a topologically ordered state, that won't be true. The partition function will count, will be related to some non-trivial topological data.
I see. So we have phases that are not topologically ordered, not protected by any symmetry, but nevertheless
Or non-trivial.
are non-trivial.
That's right. Yeah.
That's an example of invertible phases that are not SPT.
That's right. Yeah. Yeah.
Are such phases in 2+1D always chiral?
Sorry?
Invertible non-trivial phases in 2+1D always chiral?
There are, of course, SPT phases which are not chiral. non-SPT phases. That is true, I believe. Yeah, in 2 plus 1D. That's it. Yeah. In higher dimensions, there are non-chiral examples too. Yeah. All right. I'm not going to address it, but that clearly it's beyond Landau. There's no order parameter, right? I'll talk a little bit about quantum criticality in a little bit. I'm still talking about phases of matter. We'll move to quantum critical points later, right? All right. Let me move to, that was B, right? So the third step of the walk is to talk, I said non-Landau order 1 there. So now let me talk about non-Landau order 2. So I'll also call this beyond topological matter. So here, I want to discuss gapless phase of matter, right? So anything that's gapless should not be called topological. Again, it's a terminology that's often abused in the literature, but I'll declare that anything gapless is not topological. And the most familiar example is that of non-Landau order 2, of the second kind of non-Landau order, is actually very ironical. It's a Landau Fermi liquid. I think I heard secondhand that one of Steve's colleagues used to say that physics has to be consistent, but physicists don't need to be. So the best, maybe not best, most familiar example is the Landau Fermi liquid. So clearly, this has no order parameter. There's no symmetry breaking. It's obviously not topological. But there's something in the structure of the ground state wave function that protects the existence of gapless excitations. And in fact, a huge number of gapless excitations, right? So something interesting about the ground state wave function that guarantees all this, right? Now, there's interesting variants that have been of great interest in the last 15 years or so. So these are Dirac or Weil materials. Graphene is the best example, but there's 3D, many 3D examples that people have been studying as well. Now, in both these cases, despite the system being gapless, the low energy spectrum can be given a quasi-particle interpretation. Of course, you all know this for the Fermi liquid. The Fermi liquid, it's famously true in the Fermi liquid that there's a quasi-particle description of the spectrum, but it's also the most subtle case for why there's a quasi-particle description of the spectrum. In Dirac or Weil materials, it's very easy to see that there'll be a quasi-particle description of the spectrum. The density of states is very, very low, and so the scattering, interparticle scattering, denormalized to 0 at low energies. Fermi liquid is bizarre, but the Fermi liquid is familiar, right? So in these cases, there's a quasi-particle description of the spectrum. Again, only for the low energy physics. If you ask high energy questions, there's no guarantee for quasi-particle. There's something in the ground state, right? I use order to describe topological matter, right? Why? There's no order in the conventional sense. There's order in some weird sense. Now, in an even weirder sense, there's some structure in the ground state wave function in all of these that protects their excitation spectrum, right? For lack of a better word, I'll call it all order.
Like a system that involves fraction, then ground state is a superconductor.
Right, very good. So let's get around that. right? Since we just want to argue that Fermi liquids can exist as ground states, let's consider the following model. Take a triangular lattice where there's flux, let's say pi over 2 on up-facing triangles and minus pi over 2 on down-facing triangles, right? So in this model, there's no inversion symmetry and no time reversal symmetry. Then there's no degeneracy between k and minus k. So then Cohn-Ledinger is suppressed, right? Or killed. It's killed. So as a matter of principle, Cohn-Ledinger doesn't muddy the waters about the existence of a Fermi liquid. Now, in practice, of course, even without breaking time reversal and inversion, we would say that there's a huge separation of energy scales. So there's a Fermi liquid fixed point. Even though it may be unstable, lots of marginal directions that flow away, right? But the fixed point exists, right? It's good enough as a ground state, right? And that's how we treat it in most practical situations, as though there is a ground state, right? So I'm not going to worry about Cohn-Ledinger for this purpose, right? Now, there are other examples which don't have a quasi-particle description, and those are perhaps the most interesting. So the best understood, both theoretically and experimentally, is in a half-fill Landau level. It forms a metal which is very weird, right? So you have a big magnetic field. Electrons, you imagine, move in cyclotron orbits, but it forms a metal. And there's a metal, it's understood, of composite fermions and not of electrons, right? The things that form the Fermi surface are composite fermions, which are electrons bound to some 4-pi vortices. So these are seen in experiments. And in theory. And there's a reasonably good understanding of these, both from experiment and from theory. Other examples are certain kinds of gapless quantum spin liquids. Now, in experiment, it's questionable if they've been seen, but they certainly exist in theory land. Okay. And yet others, which Andy mentioned already, or non-Fermi liquids, which look like they've been seen in experiments, and there are models in theory space as well. But it's not clear that the models we can control in theory space correspond to anything that have been seen in experiments, right? But at least theoretically, there's a proof of principle that non-Fermi liquids can exist in any dimension. From experiments, it looks as though non-Fermi liquids also exist. But there's a lot that needs to be done for theory and experiment to meet. There's probably many, many surprises in this last column and big discoveries that await us. Yeah.
This reason is it separate section because we don't know the water parameters.
No. All right, let's go back. The notion of an order parameter, let me give you an analogy. Let me first explain it, and then I'll give you an analogy. The notion of an order parameter, the question of what's the order parameter only makes sense if there's a broken symmetry. Right? So there's no broken symmetry, you shouldn't ask about an order parameter. So it doesn't make sense to ask about an order parameter for topological quantum matter. Doesn't make sense to ask about an order parameter for these generic kinds of gapless phases of matter. Right? So the analogy I always give people is when people come to me and ask me, my name is Senthil I. That's my legal name. I write my papers in the name of T. Senthil. And everyone always asks me, so what's your first name and what's your last name? No, that question presumes some structure about how names are written. I come from a part of the world where we don't have that structure. So the question is, to some extent, is meaningless, right? But I make up an answer just to avoid having a long discussion.
Maybe I can ask it later, but
Yeah.
can you define for us here what you mean by a non-Fermi liquid?
Right. So there is it's a gapless metal with no quasi-particle description of the low energy spectrum.
Give us a mathematical definition. Sure. How do I distinguish between a Fermi liquid and a non?
All right. And we can distinguish it from the Landau Fermi liquid in the following way, right? You look at the electron Green's function and ask whether the quasi-particle residue is zero or non-zero, right? So that's a very clear-cut mathematical definition. At least to distinguish it from the the Landau Fermi liquid by, the property of the Landau Fermi liquid that enables this quasi-particle description is that the quasi-particle weight is non-zero.
Right. But that just proves that the electron is not a low energy.
That's right. That's right.
How do you quantify that there may not be any?
Right. Very good. So you have to look at, so you can look at particular theoretical constructions of non-Fermi liquids. And then you can ask whether you can fit, suppose you can calculate the low energy properties, right? You can ask whether you can fit it to any free particle model, right? Say the thermodynamics, can you reproduce it from a free particle model? If you can't, then probably there's no even hidden quasi-particle description. Yeah.
So it could be if there's some effective quasi-particle that's zero overlap with the electron.
Right.
Typically, there's a gauge field around. If you ignore
Right.
the gauge field, you could have a situation where it looks like a quasi-particle in the sense that it's whole, but then when you include gauge field,
Right.
fluctuations-
Right. So the composite Fermi liquid is a very good example. Yeah. Yeah. So the two-channel Kondo model, so the Maryanov fermions are zero modes that are located at the impurity, right? So really you should be thinking in terms of the scattering channels that come in, leave a Maryanov fermion behind and go out as in some other scattering channel, right? So there it's a bit complicated because it's all local stuff, right? So I'm not sure exactly where to place it in terms of a bulk mini-body case. Right? Was there some other hand up? Yeah.
So for topological order, Wilson loop expectation values for certain systems can have area law or perimeter law, right? So
yeah. So those are approximate descriptions if you have a pure gauge theory.
yeah.
Now in condensed matter physics, we'll almost never have a pure gauge theory, right? There'll always be matter fields. Then that characterization is not a good characterization.
But if matter fields are gapped, then you can integrate them out and get an effective pure gauge theory out.
Yeah, so you can talk about that, but then the real correct way is to talk about the topological quantum field theory.
Yeah.
And you can characterize this topological data that characterize the TQFT, right? You can ask about Wilson loop expectation values within that. This brings me to one of the posters. The first poster that you'll see is about knots, and one of the big things about topological quantum field theory is that it gives you a way to calculate knot invariance as in terms of expectation values of linked Wilson loops, right? So topological phases are closely connected to knots. So that's an example of some correlation function, but it's not of any local operator, right?
That is true. Like
Yeah.
operator would be a non-local operator, but I think I read a review article by McCreevy.
All right, very good. Very good. Thank you for bringing that up. I was hoping no one would bring it up because
You were hoping you did.
in my typed lecture notes, I have a footnote that is half a page long, which is a rant against that terminology. How many of you are trained as field theorists? Actually, I meant to ask before. Leo, you don't count. You're a StatMech guy. Nobody, right? So I'm going to not answer that question right now because I think I'll lose everybody else in the room. But you can read my rant in that footnote. It's a very good question. It's a serious question, but it deserves a serious answer, right? Now, let me ask one more question. How many of you are experimentalists? Apart from Peter, hands up. There's a few. Peter, Minhei, All right. I'll try to keep you on board as we go along, but ask me questions if bring me back to the ground if it becomes too theoretical. All right. Someone had a question. Yeah.
For these non-quasi-particle capital spaces, is there a good reason we should?
Let me stop you. There's no. I don't think non-quasi-particle gap phases exist.
Sorry, capital
Yeah.
spaces. Sorry. For these less set of examples, is there a good reason to expect there's some common unifying principle or framework, or could they just all be different examples that are very unrelated to each other?
Yeah, so we don't know. So, for instance, you can have a quantum critical type gapless point where the gapless excitations live at isolated points in momentum space versus things like these examples where the gapless excitations live on a surface in momentum space, and these will be very different from each other. At the very least, that will be two different cases, right? Yeah. So
But non-vector order one.
that's correct, yeah.
Difference in terms of its
I can also give you a characterization in terms of the ground states alone, because there must be structure in the ground state that supports these excitations, right? But it's easiest to picture in terms of the excitations, right? That's the simplest visualization of what's different between the two phases. But of course, it all comes down to the ground state, right? You can characterize it in terms of entanglement structure of the ground state wave function and so on. Exactly, yeah. That's right, yeah. Yeah.
For example, now that you lost data elasticity because there's gap, how do you define the equivalent basis?
You can still say that as you tune some parameter, are you in the same, do you undergo a phase transition where the universal properties change, or do the universal properties stay the same as you change some parameter? Right? And we know that in a Fermi liquid, for instance, you can change the effective mass or the Landau interactions, but you'll recognize it as the same Fermi liquid. Right? Maybe at some point the Fermi surface splits off into two Fermi surfaces, and then you say it's a phase transition. Right? That is also true, but I've not yet talked about phase transitions. Right? Sorry?
Yeah, like distinguish two phases, two different things you put it there.
Right. So there are examples where within the same phase of matter, you can have a second order phase transition that you can go around, but that doesn't affect, I don't see it as affecting anything in what I've said so far. It could be a point to make in the next thing I was going to talk about, which is phase transitions, right? I wasn't going to make that point unless someone brought it up, but you brought it up. Yeah. Yeah. Yes, non-Fermi liquids are more general than strained metals. No, strained metals, most people refer to strained metals as something that have, unconventional temperature dependence of the electrical resistivity. No, a non-Fermi liquid, I'm just saying there's no quasi-particle description of the spectrum. It may or may not have unconventional resistivity, right? So non-Fermi liquid is a more general class of state. Yeah.
Is it that near the ground state, the spectrum is additive?
Yeah, that's exactly right. Yeah. 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 All right, very good, very good. That's actually a great question. So strictly speaking, you should define these phases, on closed manifolds, right? And that's what, if you want to be very precise, and it's good to try to be very precise, So I don't think your question is obnoxious. I think it's a very pertinent question. There's no bulk gapless excitations. Now, the boundaries may very well have gapless excitations. So to avoid getting into that issue, imagine putting the system on a torus or something, right? Yeah.
Similar question about Gauss and about different people. Like you said A are basically gapless.
Yeah.
So A and C are the same.
No, good. So here the point is that I in my notes I did put in a caveat. Maybe I should have written it here. So these are gapless. All the examples here are gapless phase of matter where the gaplessness is not protected by Goldstone's theorem, right? Specifically excluding it, and that's in my notes, right? It'll be in the PDF file. What's in the file will be more precise than what's in the lecture. Right? Okay, great questions. Keep them coming. So the last category that I want to talk about, and which many people have been asking me already, I have one more board there, is on critical quantum matter. Yeah. Sorry?
Those who have a gapless emerging photon.
Right.
Where does that?
So that would be an example of a gapless phase of matter with quasi-particle excitations. Exactly. And likewise, a 1D Ledinger liquid would be a gapless phase with quasi-particle excitations, though not with electron quasi-particles. Right? Okay, so the last item is critical quantum matter. So this quantum matter tuned to a t equals 0 continuous phase transition. So the textbook example, I guess it depends on which textbook. Let's say a textbook written at least 25 years back. Really talks about phase transitions out of the first kind of Landau ordered states. So we have Landau ordered phase and a completely trivial phase, a trivial gap phase. So then there's a quantum version of Landau-Ginzburg-Wilson theory in terms of a fluctuating order parameter. Yeah, that's coming next. So this dictates that there's a field theory in terms of order parameter field. So the physics behind the statement is that goes back to Landau, who identified the long wavelength, low frequency fluctuations of the order parameter field as being the main culprit responsible for the universal critical singularities of the phase transition. So that's textbook material, right? In fact, this story that it's the long wavelength, low frequency fluctuations of the order parameter, if you know that, you capture the criticality completely. That's the sometimes known as the Landau-Ginzburg-Wilson paradigm. And all this, throughout this landscape, this is the only example where that framework works at all. Everywhere else, it completely fails. Okay? So obviously, it's going to fail if one of the two phases has non-Landau order of any kind. Right? It's not captured by an order parameter. So then how's it going to work? So the first example is where you have non-Landau order in at least one of the two phases, and out to any other phase. Yeah. Oh, just take the transverse field Ising model. ON rotor model. You know, there's lots of examples you can construct, right? So here, obviously, a very famous example of this kind of phase transition are the integer quantum Hall plateau transitions or fractional quantum Hall plateau transitions. Obviously, you're not going to describe those in terms of an order parameter field. There is no order parameter for that phenomenon. So there are other examples of this kind. You can take any non-Landau order you want. For instance, you can go from a magnetically ordered state here in a spin system going into a quantum spin liquid. It involves the onset of a broken symmetry. So there is an order parameter that captures this phase, but there is no order parameter for the spin liquid phase. So you can't describe that in terms of just long wavelength fluctuations of an order parameter. That description would be completely wrong. And we have many examples where it fails explicitly. Now, there's a particularly interesting example that's usually not put in this category, but I want to put it in this category, which is the phase transition between, for the onset of broken symmetry or coming out of a Fermi liquid, right? We've already declared that Fermi liquids have non-Landau order. So what can we expect for the phase transition between, say, a paramagnetic Fermi liquid and a magnetically ordered Fermi liquid, right? Take ferromagnetism or antiferromagnetism coming out of a Fermi liquid ground state. Now, at the very least, so, this paradigm tells us that we are going to write a theory just in terms of the order parameter field. Clearly, that cannot be correct, right? At the very least, we have to include the gapless excitations near the Fermi surface of the metal, right? So that already makes it different from the standard Landau paradigm, right? In a very minimal kind of way. So this minimal modification was first written down 50 years back by John Hertz. It's called the Hertz paradigm, subject of many, many papers. It's a very hard problem to solve. People are still working on it. And in terms of application to real materials, there's lots of experimental systems where you see this kind of phase transition between a Fermi liquid phase and some magnetically ordered phase, particularly in heavy fermion systems. The application of this Hertz minimal paradigm to describe that phase transition is not entirely clear, right? There's all kinds of questions about what the Fermi surface is doing across transition. Is it just doing what the magnetic order tells it to do, or is it doing something else? Yeah.
What if you had, some very large wavelength antiferromagnetism in a really teeny tiny Fermi surface? So that, you...
Right, you can still have, so that may be a case in which you can get away. You still have to worry about coupling between the energy density of the fluctuating order parameter and the particle hole excitations of the Fermi surface. It's depending on exponents, it could be relevant, but you have to reanalyze it, right? Yeah, exactly. So that is a good example where, so in some cases, you may be able to get away with the Landau story, but generically you won't, right? Yeah.
We have a pairing instability becomes a superconductor. Then the Fermi surface, when the Fermi liquid story is not Landau, then does that belong to that? Because it clearly has one.
The superconductor. Right. So that doesn't belong. I mean, if there's a finite coupling phase transition, so usually the superconductor instability is zero coupling instability, right? But if somehow you could stabilize it, let's say by breaking time reversal inversion, you stabilize it to finite coupling. That's not that you have to include the gapless excitation from the surface at the very least, right? So that will fit into this Hertz paradigm, right? Which is the minimal modification to take into account the presence of the Fermi surface.
Okay, so we have to add some additional
Gapless degrees of freedom. That's right, yeah. But the issue with this Hertz story is more severe than just that it's a hard problem to solve. Other things may be going on that are not captured by just focusing on whether symmetry is broken, right? The Fermi surface, in fact, people have suggested that entire sheets of the Fermi surface disappear on before the, at the same time as the magnetic ordering transition. And there's no description of those kinds of criticalities at all. At least none that it doesn't exist.
Hard descriptions.
That I didn't want to say anything more. Just beating me.
Earlier, we said that strange metals are a subset of non-Fermi liquids. But to me, that seems like it fits more into this quantum critical.
Right. So that's a great question for debate. Are strange metals necessarily quantum critical? It is true that in many experiments, strange metallicity happens in the vicinity of a quantum critical point. But there are other experiments there are other systems in which empirically you get strange metal physics over an entire range of parameters. So it's not clear that these necessarily are tied together, right? For instance, it's a matter of great debate in the cuprates whether the observed strange metal physics can be linked to a quantum critical point or not. In fact, some of us were just talking about it at breakfast. So it's a question for you guys to ponder.
Can it still be strange metal not or is there a known model?
There are known models.
For strictly people?
Sure. I mean, the composite Fermi liquid is a good example. If you want a model that's reasonably well understood theoretically and reasonably well understood experimentally, go to the composite Fermi liquid. There are other examples as well, purely theoretically. Now, finally, there's a more extreme version of this, which I only very briefly mentioned, just for completeness. Oops. Oof. How to work out? Is there a more efficient way? So this land of forbidden continuous transitions between Landau ordered states. So an example, so you have one kind of Landau order. You have another kind of Landau order. And so Landau theory has rules on when this transition can occur through a single second order transition. But there are examples where those rules are violated. So again, the best studied example is in 2D square lattice magnets, where this can be the Néel state. And this is a state that preserves spin rotation, but breaks lattice symmetry. It's what's called a VBS state. And at least, so let me write SUN magnets with n large enough. So this is a second order transition that's not allowed within Landau theory. And we know that the field theory description of it can be given in terms of a theory with emergent gauge fields and gapless matter fields with fractional quantum numbers, even though neither of these objects exist as quasi-particles in either phase. So this goes under the name of deconfined quantum criticality. Okay. So one of the reasons to talk about all of these together, walk you through this landscape, is that one thing that I've learned in the course of my career is that there's remarkably intimate connections, at least theoretically, between these different kinds of phases and phase transitions. So you may be interested only in non-Fermi liquids, right? Or maybe interested only in Fermi liquids, right? It turns out that even if that's your only interest, you'll learn a lot by studying topological phase of matter. Likewise, if you're only interested in topological matter, you'll still learn a lot by thinking more generally about broken symmetry and gapless quantum matter. And there's all kinds of interplay between ways of thinking about these different kinds of phases that show up in surprising ways when you're trying to understand one aspect of one of these phases of matter, right? So it makes sense, therefore, to think about all of them, right? And develop sort of a global understanding of all of these. And you never know when in the future, which insight you can draw upon to make progress. Okay? Yeah, 10 minutes? Okay, I can just get started on the thing, which is some examples. Yeah?
I mean, I know you have this little subtlety about we need n large enough.
Yeah.
Is there, at this level of analysis, is there any insight you can offer about when these might be second order transitions?
No, because this for the SU2 magnets was a subject of 20 years of numerical work, after which it's finally become clear that there's a very long correlation length, but it's finite. I think of it as a cruel joke played on humankind, but that's so be it. It looks so continuous, but people have looked at it very, very carefully, and it drifts, exponents drift, and so on. Yeah.
I mean, an important point there. Does it have to be first order? It could always be first order.
Anything can be first order, at least without disorder.
Is there a principle that's driving it first, that requires it to be first order?
No, not in this example.
But for any of these, like, should I say likely to be first order for some of these more exotic transitions?
Yeah, so that's a great question. It's a question I've grappled with for a long time. I'll give you a very simple example. I think the answer is it's going to be first order, but I can't definitively say so. If you take a mode transition from let's say, some lattice with no nesting, being a fixed, let's say, half filling, you go from a Fermi liquid to an antiferromagnetic mode insulator. The conventional Fermi liquid and the conventional mode insulator. Can that be a second order transition? My guess is probably not. But I can't prove it. I can't prove that there's no weird theory that somehow manages to give this in a second order way. And there's similar questions which are at the heart of many of the issues crippling progress in heavy fermion criticality and the observation of strange metals there. Now, there may be a phenomenon called Kondo breakdown that's going on. It's been postulated at least, where the Kondo screening that gives you the heavy Fermi liquid is postulated to disappear at the same time that magnetic ordering onsets. Now, those are words. Now, can that go through a second order transition as has been postulated? I don't know, but I can't prove it one way or the other, right? So we'll see. The one other thing that I've learned over the years is that intuition for which transitions can be second order and which transitions can't is very poor. I'll give you one more example of this kind. So this textbook example, where you go from Landau order to trivial order, say, okay, here we are safe, right? But it turns out there's an example where even for this, there is a new universality class, which is beyond Landau, right? Where the low energy physics is not captured in terms of fluctuating order parameters. So even in this case, it's not guaranteed that standard Ginsburg-Landau theory works. once we found one example, you worry that maybe it's not generally true. Right? It's not that complicated. Okay, it is complicated. It's an example with NF fermions coupled to SUN gauge fields in 3+1 dimensions. And there's one phase which is a completely trivial gap phase. There's another phase which is completely trivial except for the fact that it breaks time reversal spontaneously. So you expect an Ising transition. But instead, the Ising transition is of course possible, but there's another fixed point which has gapless emergent fermions coupled to gapless gauge fields. No, that's a completely different fixed point, right? And it's locally stable. You only tune one parameter to reach it. So once you find one example, you worry that maybe we can't have too general a rule.
Elaborate on your comments about not being able to exclude that being second order. So let's say I said it's second order and it's conformal. Then and I make some conjectures about the symmetries of the conformal field theory and how many operators I have that are relevant with various symmetries. Then I can exclude conformal field theory. Yeah, so in fact, that's some of the evidence for SU2. Because through years of work, we understood that this, for SU2, that this critical fixed point, if it exists, will have an SO5 symmetry. And then you can, with some estimates for various exponents and so on, then you can run conformal bootstrap to ask whether there's a stable fixed point with SO5 symmetry that fits that requirement, and there isn't. Well,
right?
Were you saying that one can't exclude that it's some other conformal field theory that doesn't have the SO5 symmetry?
No, so for the lattice models that people have studied, the data very much points in the direction of a weak first order transition. Now, there may be other fixed points out there which have completely different exponents. No, that'll be the unknown unknowns, right? So we can't say anything about.
But lattice model.
Yeah.
Am I allowed, like, these results about conformal field theories, do they exclude a conformal transition between nil and BPS?
No, they can't, right? Because the way conformal bootstrap works, you need to know something about the rough exponents and then look for a solution to those crossing equations. But if you tell them exponents can be anything, right? So then they have no way of telling you anything. Right?
So it's not a question about not having SO5. It's
Yeah.
a question about, it's just a practical matter that you can't check for all possible exponents.
Exactly, yeah. All right, have 5 minutes. I can maybe get started. I want to say some very simple things, which will set the stage for tomorrow's, not tomorrow, whenever I'm speaking, Wednesday's talk. So the first thing I want to do is topological insulators revisited. Okay. The one thing I'm not going to do throughout my discussion of topological insulators is to mention the word band theory, right? So we'll discuss it without band theory, right? Completely. So let's consider, sorry? Yeah, I'm not even going to specify the Hamiltonian, right? Hamiltonian free discussion. Why not? It's topological. So consider an insulator in 3D with excitations that are only electrons or their composites, meaning there's no anyons, no fractional charge, nothing, right? So I want to ask about some general structure of these insulators. And so I'm going to assume time reversal and charge conservation symmetries. So there's a global U1 symmetry. And as usual, that the electric charge is T even. Right? That's the usual story about electric charge. Yeah?
What is the electrons or the composites? I guess like
Super pairs, trions.
I guess how would you distinguish
Oh, anyons cannot be made locally by bringing together any finite number of electrons. Yeah. Okay. So I want to write down some trivial observations about this system, and then I'll stop. And a big homework problem for you is to see how much you can run with these trivial observations. And if you don't run, I'll do the running for you in the next lecture. So we know that all the excited states can be labeled by the electric charge because charge is conserved, right? And they must have integer charge by decree, right? We don't have anything else. We don't have fractional charge in the system. So excitations with charge NE, N belongs to Z, right? These are the integers. And if N is odd, we know that this excitation must be a fermion, right? And if N is even, it must be a boson, right? So hopefully this is all good, right? So this observation is going to play a crucial role in the rest of the story, right? So I'll give you one hint on where I'm going, and then I'll stop, right? So we're going to probe this medium in a way that no experimentalist can ever probe it, right? But what the heck, we're theorists, we can do whatever we want. So let's probe it by catching a magnetic monopole and inserting it into this medium. No, it's a completely legal theoretical probe of the system, even if it's impossible for the best experimentalists in the world to do. Good, very good. That's the spirit. Love it. All right. Gedanken experiment. As a probe, place a magnetic monopole and presumably you all know that in the presence of electric charges, magnetic monopoles are quantized. There's a famous argument by Dirac, right? So the basic strength is H over E, and I'll call this 2 pi in units where H bar and E are set to 1. The medium. So I want to emphasize that this is a probe of the system. There's not a quasi-particle excitation in the system, right? There's just something I come from the external world and use to probe the physics of the system. Now, let's think about time reversal and monopoles, right? So electric charge is even. So electric fields are, of course, even under time reversal, but magnetic fields are odd, and therefore magnetic charge is odd, right? Now, suppose the monopole picks up some electric charge when I introduce it as a probe of the system, right? So this is the charge that's nucleated around the monopole, right? Now its time reverse counterpart it could be 0, but in general, it could be non-zero, right? Let's allow for the possibility that it's something. Yeah. So if you measure the charge of the associated with the monopole, everything is gapped, but locally there may be a charge, right? Now by time reversal symmetry, its time reverse partner must have the same. Right? So I have a monopole with magnetic fields coming out, have the time reverse monopole with magnetic fields coming in. And now I want to imagine bringing these two things together and getting rid of the magnetic charge. Why not, right? I take my monopole and its time reverse counterpart. They have opposite magnetic charge. I bring them together till I get rid of the magnetic charge, right? So when I bring them together, I'm going to have an object with no magnetic charge at all, but it'll have an electric charge of 2 times QE, right? Now, once the magnetic charge is gone, this object must be an excitation of the system, right? And this excitation must have an integer charge, right? So I need to stop. So let me just tell you that this means that this charge, there's 2 ways in which it can have an integer charge. The combination of these two, QE can either be quantized to be an integer or it can be quantized to be an integer plus a half, right? So just based on these considerations, you'll conclude there's 2 distinct kinds of insulators, right? Now, I'm going to run with this in the next lecture and show that this implies all kinds of things. It implies that topological insulators exist in electronic systems where the charge carriers are fermions. I'll prove that charge carriers need to be fermions. I'll prove that they need to be Cramer's doublets in time reversal. And I'll prove that they need to be spin-orbit coupled, right? And all of this will just come out of just what I've told you so far and without invoking any Hamiltonian, right? I didn't write it out in words, but the point is that this combination is a quasi-particle. So it must have integer charge, right? So in principle, so 2 times QE equals integer. So QE can either be an integer or QE can be a half integer, right? And any integer is equivalent to any other integer because I can just add electrons. And any half integer is equivalent to any other half integer. I can add electrons. There's 2 distinct classes of solutions, right? Either QE is equal to 0 mod 1 or QE is equal to half mod 1.
So it means when you were adding kind of another equivalent statement is when you're adding a monopole, or you actually bound a half an integer charge.
Yeah, I won't say bound, nucleated. It polarized the medium so that there's half integer charge associated with it. And that'll be the topological insulator.
More direct conclusion would have been that it just has 2 times QE.
No, but these arguments allow it for it to be half. That's consistent with time reversal and charge conservation. Right? Let me. So this is just supposed to be a preview of coming attractions, right? I'll expand this, elaborate on this. Yeah. You can call it a dione, yeah, but I don't need to use that word, right?
Experts tank Senthil.
Yes, this is like in one dimension, like the solitons.
Yeah, absolutely, yeah, that's right. Right. So with